Hello everyone and welcome to TLE Eliminators. Today we are going to do the PCD for Codeforces Round 1029 Division 3 contest. Before we get started, can someone confirm in the chat that I'm audible, and then we'll get started right away. We're going to be discussing CF Round 1029 Division 3. Someone quickly confirm in chat if I'm audible or not, and then we'll get started. Okay, cool. So before we start the session, we'll do it slightly differently for the same way we did today morning session on lead code. First we'll discuss the problems. So today we're going to discuss A to F. All right, we're going to discuss all the problems A to F, and then after that, no, we'll start from A itself, Dushyant. Unfortunately, that's the way we do it. So we're just going to start from A and go up to F because everyone is stuck at different points. Okay. And then at the very end, we will have a general doubt session where you can ask any general doubts you have related to CP or related to your journey, not related to the questions. And I will answer all of those at the end. Okay. So let's start with problem A. Don't worry, I'll finish A and B pretty fast because I think most people got it. It won't take too much time, all right? Okay. Problem A, Yusuf is at the entrance of a long hallway with okay, yeah, before starting, I just want to say, if you're struggling with contests or you're feeling like you're not progressing or you need some help, then do check out the TL Eliminators course. We are having a self-paced course running right now with 3 different levels. Each level covers different topics, based on like your current level. And it goes all the way from beginner to intermediate, pre-intermediate, advanced. So take whatever is, you can always go here and take whatever is appropriate for you. And this is made by some of the best competitive programmers in the country with more than 40 hours of recorded lectures, curated practice problems, doubt support by high-rated mentors, including myself. Each problem has detailed hints and video solutions. So for all this and more, definitely check out the TLE self-paced course. All right. Okay. So now we'll start problem A. False alarm. Yusuf is at the entrance of a long hallway with n doors in a row numbered from 1 to n. He needs to pass through all the doors from 1 to n in order of numbering. So each door can be open or closed. If a door is open, Yusuf passes through in 1 second. If a door is closed, Yusuf cannot pass through it. However, Yusuf has a special button which he can use at most once. This button makes all closed doors become open for X seconds. Your task is to determine if Yusuf can pass through all the doors if he can use the button at most once. Okay, so let us understand the statement. Let us take an example. So we have 6, 3, or let's take the first example 4, 2, 0, 0, 4, 2. This is problem A. Problem A. So we have 4, 2, and the 4 doors have the following states. Okay, so open, closed, closed, open. And our button can open a door, like open all the doors for 2 seconds, right? So here the straightforward observation is if we press the button, we can pass through the next K doors, whether they're open or closed. Initially, we can pass through the next K doors. Okay. So what does this mean? This means that when we start, if we ever encountered a closed door, so let's say we started here, we encountered a closed door. If we press the button, then we can go the next 2 doors and then we can continue the journey, right? That's what this means. But we can press this button at most once. So what does this mean? This means that if, for example, instead of this, the test case was something like this and K equals 2 itself, then when we come here, we press the button, we go through this door and go through this door, but here we'll get stuck, right? So that's the key idea. So the code for this is also pretty simple. All we need to do is we need to check if the first one and the last one, whether the distance between them is less than or equal to k or not. Okay. So in a given array, let's say our test case was something like this, and k equals 8. Okay, k equals 8. Then what we need to check is we need to check if we find the first position of 1 and we find the last position of 1, then if this distance which is there, if this is less than or equal to 8, then we know that the distance between these two points is less than or equal to 8. Okay. So hello everyone. Very sorry about that. Can can you hear me? Hello. Can someone just tell in the chat if I'm audible? I'm sorry about that. There was some internet issue. Okay. So how much was missed? Like, I guess the explanation of A was covered, yes? The code I was covering? Yeah, okay. So again, in A, we need to find the position of the first occurrence of 1, the last occurrence of 1, and then we need to check if that is less than or equal to K. All right. And this is because if we press the button, we can go through the next K doors, and that's the only way we can go through the doors. So simply we find the last position of 1, the first position of 1, subtract them, and check if that is greater than equal to, that's less than equal to K. In that case, we print out yes, otherwise we print out no. Okay, can we move on to the next question? A was going on, okay. Right. So let's move on to the next question. I'm sorry about the internet issue. I think the explanation for A is pretty simple, so it should be understandable with this much itself. Okay, problem B. All right. Shrink. A shrink operation on an array A is defined as follows. Choose an index such that A of I is greater than A of I minus 1 and A of I is greater than A of I plus 1. Okay, so it's greater than both the adjacent elements. Then remove A of I from the array. Define the score of a permutation P as the maximum number of times you can perform the shrink operation on P. Okay, Yusuf has given you a simple single integer n. Construct a permutation P of length n with the maximum possible score. If there are multiple answers, we can output any of them. Okay, yeah. So how do we solve this? Well, let's take a look at the examples and understand the question. Okay, the first thing we can say is for the first problem, the time complexity was obviously big O of n, right? So nothing much to discuss. This is problem B. Problem B. Okay, right. So we can choose an index. So let us take any permutation, something like this. Okay, so we can choose any index such that both sides are greater. Both sides, like it's the element in the middle is larger than the element on both the sides. That is, it is greater than both the adjacent elements. So, for example, let's change the permutation. So if we have a permutation something like this, so 5, and then we have 4, 3, let's say 2, 1. Okay. So what we can do here is we can, since 5 is greater than 4 and 5 is also greater than 3, then we can remove 5. And this is called our shrinking operation, right? And then again we get 2, 4, 3, 1. Now since 4 is greater than 2 and is greater than 3, we can remove and we get now 3 is greater than 2, 3 is greater than 1. So again we can remove 3 and we get 2, 1, right? So this is the question, and the question is n is greater than equal to 3. So pay attention, n is greater than equal to 3. And we need to output any permutation that maximizes the number of shrink operations. Okay. So how do we solve this? Well, I'll directly tell you the observation or the intuition. The intuition is put the smallest numbers on the corners. Put smallest numbers, which will always be 1 and 2, right? In a permutation, the smallest number is 1 and 2. We'll put them at the corners. Okay. And what does this do? And like, why are we doing this? Well, the idea is simple because we want everything in the middle to be reduced, right? So we're going to try to reduce everything to 2 elements remaining. And why are we trying to reduce everything to 2 elements remaining? I'll show how. So we'll put the smallest elements in the corners. And then what we can do is we can have either like 3, 4, 5, 6, 7, 8 like this, or we can have it something like this 8, 7, 6, 5, 4, 3, 2. So we can either do it like this or like this. Obviously, we can reverse these two also. We can put 2 in the start and 1 in the end. So like either we can print this or this. And This will be our answer. This is a valid construction. And I'll show why this is a valid construction. Okay. So if you observe, our operation is if we have an element which is bigger, surrounded by smaller and smaller, right? Then we can remove this element, right? And I claim that we can remove from a permutation of size n, from perm of size n, we can remove n minus 2 elements using the shrink operation. Okay, and this is my claim. How do I prove this? Well, if you take either of these two constructions, so I'll take the first one itself. And let's say I have my construction like this, 1, and then 3, 4, 5, 6, 7, let's say till n, and then I have 2, right? And for each element which is in this, right? Each element which is just before the 2, on the left, obviously the element will be smaller because it's in ascending order, right? So on the left, the element will be smaller, and on the right also it will be smaller. So we can keep removing this element using the shrink operation. Like it will become something like this: 1, 3, 4, 5, 6, 7, n minus 1, 2. Then it will become 1, 3, 4, 5, 6, 7, n minus 2 till 2, like that. And then eventually it will reach 1, 2. Like all these elements, they follow the same rule that the previous element, because it is the previous element in ascending order, it will be smaller. And the next element will be 2. Like we'll pop one by one like this, right? So next element will be 2, so it'll be smaller. So we'll eventually get the array 1, 2. If you do it in this way also, the same logic applies. You can remove 8 because 1 is smaller than 8, 7 is smaller than 8. Then we can remove 7 after that. So then we can remove 6, 5, 4, 3 until we reach 2. And any of these patterns work, even reverse of this pattern works. And we can print that as our answer. And then this becomes a simple pattern printing problem, which can be solved in time complexity of O of n. Yeah, that makes sense. Yeah, 1, 3, 4, 5, 6, 7, 2. That will also work, yes. Hmm. Yeah, a lot of people did a lot of different patterns. So there might be more than one pattern. Yeah, 1, 3, 4, 5, 6, 7. Yeah, that Raghav, yours will work. And red and 9, 9. You did odd numbers and then even numbers. Hmm. Yeah, yours will also work. So yeah, there are a lot of patterns which will solve this. Okay. So I'll just show my submission for B. Right? It's very simple. We make an array. We fill the array from all the numbers from 1 to n. Then we swap the first element with the element position 2 and last element. And we simply get this pattern. This first pattern which I described, we get that pattern. And we simply print that out. So we swapped the position, we swapped the for the second element with the last element, right? So yeah, this is also a slightly different pattern which I did in the contest. So there are many ways to solve it. Yeah. So the way I did it was I swapped 1, 2, 3, 4, 5, 6, 7, 8. So I swapped this and this. And what will this do? This will give us something like this, right? And here also you can observe that this, like because 7 is greater than 2, 7 is greater than 6. We can cancel 7, we can cancel 6, 5, 4, 3. We can cancel till 4. Then since 1 and 3 is greater than 8, we can cancel 8 and then we can cancel 3. So there are many ways to print the pattern out. You can choose any of the 5, 6 ways. Like right now itself, we discussed 3 ways. In the comments, people are giving more than 5, 6 ways to print it. So yeah, okay. Yeah, please don't spam D, guys. We'll currently go on to D. Okay, moving on to C. let's move on to problem C. Okay, problem C. If anyone has any doubts with B, please tell me. Otherwise, we'll move on to problem. Okay. Korshan, we're currently on problem C. Everyone is fine with the explanation of B, right? Yeah. Yusuf has an array A of size n, and he wants to partition the array into one or more contiguous segments, such that each element A of I belongs to exactly one segment. Okay? A partition is called cool if for every segment Bj, all the elements in Bj also appear in the segment Bj plus 1. If it exists, that is, every element in a segment must also be present in the segment which is following it. Okay? So for example, if 1, 2, 2, 3, 1, 5, then a cool partition is 1, 2 and 2, 3, 1, 5. And why is this a cool partition? It's a cool partition because every element in B1 is present in B2. Okay. So after partitioning the array, we cannot change the order of elements. And yeah, even if an element appears several times in some segment, it only needs to appear at least once in Bj plus 1. Your task is to help Yusuf by finding the maximum number of segments which make a cool partition. And I think uh, this is, yeah, this is pretty straightforward. Like this is not very straightforward compared to the previous question, I think. In fact, I think D was also easier than this, right? So let us go over what the problem is asking us. So it is saying if we have an array like 1, 2, 2, 3, 1, 5, right? So we have an array like this. Our idea is we need to divide this into contiguous segments. So basically, what are contiguous segments? Contiguous segment is nothing but subarrays. So we need to divide it into subarrays. Okay. So divide it into subarrays. Okay. So we need to divide it into subarrays. What else do we need to do? We need to make sure that for each subarray we make, okay, so let's say we made two subarrays. All the elements which occurred at least once here also occur at least once in the next subarray, and so on. So basically, for each subarray, all elements which occurred previously also occur here. Okay, that makes sense. So how do we do this, and what is the intuition we should use here? Well, what we will do is we will try to use greedy. Okay, so this is going to be our intuition. Our intuition is use greedy. Okay, and what greedy should we use? Well, we know that we know that we want max number of subarrays. So when we build the subarrays, we will try to keep them as small as possible. We will try to keep them as small as possible. As possible. What do I mean by this? What I mean is, if you take the first example, if we take the first example, which is 1, 2, 2, 3, 1, 5, right? This is our first example. we will try to keep it as small as possible. And what that means is, okay, this is a valid splitting. This is a valid splitting because one occurs over here and here, two occurs over here and here. But what we will do instead is we will take for the first subarray, it will always be the first element itself. So that's as small as possible for the first subarray, right? And the second subarray, we will go on until we find a one. We cannot close it here because there is no three yet, right? And there is no two also. Like we'll try to close it here, but then what happens is like here we cannot get a three, we cannot get a two, we cannot get a one, right? So then we end up with our answer is this whole till five, and our answer becomes two, right? And what we're doing is we're trying to build the first subarray as small as possible. And then the next subarray also, we'll try to build it as small as possible. And let me give you another example for that. Okay. So let's say we had one, then two, one, uh, two, right? And then three, two, one, something like this. Okay. So what we'll try to do here is first we make this as our subarray. Okay. Then here we start until all the elements of this subarray are covered, we'll extend. Otherwise, we'll not extend. Okay. So one is not covered yet. So we extend it, right? We go here. Now one is covered. So we stop. We stop here itself. We don't go further. Okay. Now here we go. Here we have two. So here we need to cover two and one, right? So here we have two and that covers this. Three doesn't cover anything. Two doesn't cover anything. One covers this. So then we get our answer is three for this test case. Okay. So each time we are trying to keep the minimum number of arrays in our subarray. Like we could have tried to extend more. We could have tried to extend more. And in fact, this is also a valid answer, right? This is also a valid answer because there is one, there is one, two, there is one, two, and three, right? So each is covering the previous, but we are going to stop it as soon as possible. And we can see that this greedy method of stopping the subarray as soon as possible, as soon as the previous one has been covered, it works because the answer can never get better than what we get from this method, right? So this is the intuition. Did everyone get this intuition or should I explain it a bit more? Since we want the maximum number of subarrays, we'll try to stop it as soon as possible. And this has two advantages. It leaves more elements remaining, leaves more elements remaining. And in the elements, we need to check for the next subarray, like less elements will be required in the next subarray, right? So it's giving us both benefits in the problem. So this greedy approach is correct, right? Right. Okay, how will we know to stop in the first? Okay, we'll get to that, right? Vibe hai, okay, someone asked a particular text case, so I'll show it. Let's say we have 1, 2, 1, 2, 1, 2, 1, 2. Okay, 1, 2, 1, 2, 1, 2, 1, 2. Who was that? Manash Koi. Okay, something. Yeah, so let's see. Um, one, yeah, okay. So if for this we need to split, so obviously we start the first element here. Then the second subarray will be like this, right? Because we need to cover the one of the previous one. Then the third subarray, we covered the two here. Now we're covering the one here. So it'll be like this. And then here we covered the two here. We covered the one here. So it'll be like this. Here we can't get a one. So basically our final answer is simply going to be like this. And our answer will be 4 for this test case. And this is what we mean by stopping the subarray as soon as possible, right? Okay. Now our second part is how to check if we can stop the current subarray. Okay. How to check if we can stop the current subarray? Right. So we already decided that we will stop as soon as possible it is to stop. But how do we check if we can stop it or not? Okay. And the idea is maintain a set of elements. Okay. Maintain a set of elements such that maintain of set of elements, which is it contains all unique elements of the previous subarray Okay. When we see this element, erase it from the set. Okay, so in our current subarray, erase it from the set. Then simply when the set is empty, we can stop. Okay. What do I mean by this? Let me show you with an example. Okay. So let's say our array was 1 followed by, let's say, 4, 5, 3, 2, 1, then 6, 7, 4, 3, 2, 5, 1, 8, and so on. Okay, so this was our array. So what we do is, so this first element, of course, is its own set. So here we have a set. Okay, so once we start a new subarray, we will have the set of all elements which appeared so far. Okay, so we'll have the set of all elements which appeared so far. So our set will look like this. Okay, so now where we are 4, since 4 is not in the set, we do nothing. Okay, so 4 is not in the set, so we do nothing. 5 is not in the set, so we do nothing. 3 is not in the set, we do nothing. 2 is not in the set, we do nothing. 1 is in the set, right? 1 is in the set. So since 1 is in the set, we remove it. Now our set is empty. And when our set is empty, it means we have covered everything of the previous subarray. Correct? We have covered everything of the previous subarray. So all we need to do is close this here so we can start a new subarray, right? Then here again we start. And then what happens to the set value? Well, in the set, we just need to add all the unique elements in this range. And actually, you can show that it's simply equal to all the unique elements in this range, right? Then we can start over here. So what is our sets value right now? Our sets value will be 1, 2, 3, 4, 5. So for Java users, I guess you don't have set data structure. So it'll be something like tree list or something. Yeah. So here we start at 6. So 6 is not in the set, so we do nothing. 7 is not in the set, we do nothing. 4 is in the set, so we remove 4. 3 is in the set, we remove 3. 2 is in the set, we remove 2. 5 is in the set, we remove 5. 1 is in the set, we remove 1. Okay. And once everything is removed from the set, that means we covered everything which appeared earlier, right? 1 appeared earlier, 2 appeared earlier, 5 appeared earlier, so on. We covered all of them. So now we can move to the next. We can close this subarray and try to make the next subarray. Okay. So if we can't ever make a subarray, let's say it ended over here, then the answer will simply be 3, right? And that's how we're going to figure out the answer. And what will be the time complexity of this? The time complexity of this will simply be, so each time we are going through the set, right? So our complexity will be at most, like each time we're going through from I equals 0 to I equals n minus 1. And then when we are creating a new subarray, we are covering this distance again. So the previous subarray again. So the total number of operations basically will be roughly 2n, right? Number of set operations will be roughly 2n. So because of set operations work in log n, right? So set operations will work in log n. So our answer will be we go of n log n complexity, right? And I hope this was understandable what I just explained here. Basically, we're maintaining a set which for the previous subarray we made, it has all the elements stored. Okay, it has all the unique elements stored. Then when we go through the next subarray and we start deleting the elements. So as soon as we see the elements, we start deleting from the set. And as soon as the set becomes empty, we have formed this subarray, and then we can move to the next subarray. Does that make sense? Okay, how is the time complexity 2n? Okay, I'll tell you why it's 2n. Because we have 1, 4, or let me just use this example directly, all right? So here, when we're going I++ and the set is not empty, right? So it's simply I++, so it's simply big O of n, correct? So it's simply big O of n to do I++, right? Now, once we form a new set, so from here onwards, we need to form a new set. So we need to fill the set with all the unique elements before, correct? We need to fill the set with all the unique elements before. That means we need to fill the set with all the unique elements in this range, right? So first we went up in this range. Now we're coming back down in this range, right? So for each range, we're going up, then we go back down, then we go up, then we go back down, then we go up, then we go back down. So each value is being visited at least at most 2n times. Like each value is being visited 2 times. So the total operation is at most 2n. Does that make sense? We can make two sets, current set and previous set, and the time complexity will be same as copying the sets. No, it will not be the same as copying the sets. Why is that? It's because of this reason which I explained here. The reason is that when you copy the set, that method is also correct. When you have two sets, current set and previous set, right? So assume that you swap previous set and current set every time you start a new subarray. Then you delete stuff from your current set until it becomes empty, and then you repeat that, right? The complexity will not be big O of n because your current set, your current set, it will contain at most the number of elements which were here, right? It will contain at most the number of elements which were here. And that basically falls under the same argument. It's like going front and back in the array, front and back in the array, front and back in the array. So each element is being visited twice. So even though you're copying, you're only copying elements which are less than equal to this, right? The number of elements being copied is less than equal to this segment, right? So this length, let's call this length L. So the final time complexity is just n plus n or big O of n itself. Even the set methods in which you do copy and stuff. Is it possible to calculate from frequency? Definitely it is possible to calculate from frequency. Instead of a set, you can use a map. But the only frequency you will get is 1 and 0. So there's no point using a map. But obviously you can use a map as well, no problem. Because you don't care about frequency more than 1, right? If any element has frequency more than 1, it's the same as if it had 1, right? So it does not matter. So did everyone understand the time complexity? Yeah, this is linear time itself. So if you use unordered set, you can do this in linear time. If you use set, it will be n log n. I hope the explanation was understandable. If any doubts, please ask. Otherwise, I'll move on to D. So what was our idea? We'll try to build the subarray as small as possible. Then that's why that helps us maximize the number of subarrays we can. How do we find out if we can end a subarray? We simply hold a set of everything visited so far, right? We simply hold a set of everything visited so far. Every time we start a subarray, we start deleting stuff from that set. When that set becomes empty, we know that we visited everything so far. So we can start a new subarray at that point. And then what happens? we can show that this is at most 2n operations of the set, so it's n log n complexity. And how can we show that it's 2n operations? It's like going front and back to each subarray we created. Why front and back? Because front we're going to delete elements, back we're going to add the elements again, right? So let's go to the code for this. Yeah. So first we take in the vector A, each element, right? Then we have two sets. So the way I implemented this was two sets. I didn't want to go front and back, like that is just for the proof. So one is previous, okay, which will hold the values which we need to delete. And total is from all the elements from the start till now, okay? And then, yeah, part count is how many parts we have split it in. At first it will be 0. So first we'll insert the element into total. So if you observe, total simply means all the elements so far in a set. So all the elements so far that is stored in the set total, okay? And then what do? We do, if it is there in previous, like if we need to delete this element, right? If this value is there in the set, a of I is there in the set, we delete it from the set, okay? And if the set size, if the set size becomes 0, then we can say that we made a new partition, right? So we increase the partition count and we set previous set equals total set, okay? So previous set equals total set, so that now again we can start deleting for the new subarray. And why does this take, instead of big O of n, this will not take big O of n, amortize the whole thing will itself be n only. And why is that? Because this adds at most elements which are length of the partition we made, right? So since each element which we saw so far must have occurred in the partition, the number of elements it is copying is at most the elements which were there in the partition, right? So the person who asked if they'll get TLE on this after system test, no, you will not get TLE after system test. It's because secretly, if you view in amortized complexity, the complexity of this is only 2n. And because we're using set operations, it will be 2n log n or O of n log n. All right. Yeah. Okay, we're going to D now. Okay. Any further doubts in C, or we'll go to D? C was a bit tricky, so I hope if you did not understand it, please just rewatch this video and my arguments and read the code. I think you will understand it, especially the time complexity part. To show the time complexity is not easy. To come up with the logic is easy enough. Okay. How to solve problem D? Yusuf wants to explode an array A1 to AN. An array gets exploded when all of its elements become equal to 0. In one operation, Yusuf can do exactly one of the following. For every index I, decrease A of I by I. For every index I, decrease A of I by n minus I plus 1. Your task is to help Yusuf determine if it is possible to explode the array using any number of operations. Okay? Okay, so how do we approach this problem? Let us take an example array 3663. Okay, 3663. We need to make this array equal to all zeros. Okay, make it equal to all zeros. And what are the operations? We can minus I from each element. So from first element, we can do -1. From second element, we can do -2. From third element, we can do -3. From fourth element, we can do -4, right? Similarly, we can also minus by n minus I plus 1. Okay, what does that mean? That means from first element, we can do -4. From second element, we can do -3. Third element, -2. Fourth element, -1. So either we can subtract the index or the reflection of the index, and we have to make the array equal to all zeros. And one more important idea is this will do it for every index, right? So if we do an operation, that means the operation will happen for every index. Okay. What is the assumed rating of D? Right. Assumed rating of D, yeah, 1200, 1300 will be correct, I guess. I could do the logic of C. Actually, I think D might even be 1000 or 1100 also. I'm not very sure. It might depend on how people solved it. Because the idea itself is very simple. I think C was harder than D. I could do the logic of C, but I calculated the time complexity wrong. Yeah, that might have happened. That's unfortunate. Okay, so we want to make this all zeros. So first thing we can say, first intuition which we have, intuition one. Okay, order of operations does not matter, right? Because we're simply doing uh, subtractions. Order of operation does not matter, right? First we can do this operation, then we can do the other operation. That does not matter. Does not matter. And there are only two type of operations which we can do, right? And there are only two types of operations. Two type of operation. Okay. So what should we do is, let's assume, okay. Let's assume we did x1 operations of the first type, okay. X1 operations of the first type, x2 operations of the second type, okay. So what does first type mean? It means the minus I operation. Second type means minus n plus I minus 1. So that operation, right? So what does that mean for our array? Okay, so our array is something like this, okay, an. And if we do the first operation on the first element, it will be like we did it x1 times, right? So it will be like minus x1 multiplied by 1, right? And this will be minus x1 multiplied by 2, because x1, each time we do the x1 operation, we're subtracting by I, correct? So if we do it x1 times, then we're subtracting it x1 times, right? So we can write the equation like this, okay? And what about the other part of the equation? We can do n minus I plus 1 also, we can subtract. So how do we do that? We can also write minus x2 of n minus I plus 1, okay? And this equals 0, right? Because we need to make it all zeros. Similarly here, it will be n minus I plus 1. So at 2, n minus I plus 1 will simply be n minus 1. And at 1, it would be simply n, right? So at 1, it would be simply n, right? And then x2 times n minus 2. And we get this system of linear equations, okay? And the unknowns, number of unknowns are simply two unknowns, okay? So there are two unknowns, n equations, okay? So what we can do if we have two unknowns and n equations, we can simply pick any two equations. We can simply pick any two equations. So I will pick the first two. You can pick any two you want, maybe first and last, or however you want to do it. I will pick the first two equations, and I can solve for the values of x1 and x2, correct? Anyone who has studied algebra, basic algebra, will know that system of linear equations can be solved like that, right? So, okay. What will we do here? Let us write the equation again. So our equation is a1 minus x1 minus nx2 nx2. So nx2 equals 0, right? Then we can write a2 minus 2x2, which should be x1 here, right? So this is our equation. Now what we need to do is simplify for values of x1 and x2. So should I write the simplification or not? I think Almost everyone watching the stream can do it, but I'll just write it in case, right? Right. So now if we do, take 2 times of the first equation, right? So take 2 times of the first equation. So let this be equation 1, let this be equation 2, and subtract it with the equation 2. Okay. So 2 times of this subtracted with this, and what does that become? 2a1 minus a2 equals 2x1 minus 2x1. So that gets cancelled and becomes 2n minus n minus 1 x2, right? So we get 2a1 minus a2 equals n plus 1 x2, right? Or we get x2 equals 2a1 minus a2 by n plus 1. Okay. So we found our first unknown, right? We found our first unknown. Our second unknown is simply, we can find our second unknown simply by taking this equation itself. So we can write x1 equals a1 minus nx2. So we can write x1 equals a1 minus nx2. And this is how we found the second unknown. So we need x1 operations of the first type, x2 operations of the second type. Okay. Now, of course, if this value is not divisible, right, we will get some fractional answer, and fractional operations are not possible, right? So in the case we get fractional, it will be not possible. In the case we get negative, so obviously negative operations are also not possible. If this is negative or this is negative, then again it is impossible, and we can simply print no, we can print no in that case. Otherwise, if we get valid values of x2 and x1, we can check with all the elements. Like once we have solved these two, we need to check the value of x1 and x2 for all the equations, right? So if it is satisfying all the equations, then we can say that yes, or otherwise we can say no. Okay. So does that make sense? It's very straightforward, basic algebra question. I think rating of D problem will be 1200, in my opinion. Okay. So how do we write the code for this? Um, yeah, so first we take all the values, okay, of A, right? Now we are checking if it is if the first value, so we're first calculating the value of x2. Like I explained, we're calculating the value of x2. So we try 2a1 minus a2. So since in my code it is 0 indexed, it will be looking like this, right? So we're checking this. We're checking if it is divisible by n plus 1, and we're also checking if it's negative. So if it's negative or if it's not divisible by n plus 1, then we can simply output no, right? Otherwise, we got our value of x1, x2. Then from that, we can get our value of x1, right? It's the exact same equations which I wrote here, right? Then if x1 is less than 0, so it's a negative. So that also is not possible since negative operations of x1 type are also not possible. So we simply print no. Otherwise, what we do is we go through all the equations. So from all equations from 1 to n, or actually you just need to check from 3 to n, and we check if x1 operations of first type and x2 operations of second type, if that makes it equal to 0. If at any point it does not make it equal to 0, we can make our flag equals false. Then we can simply print yes or no based on whether a flag is true or false. Does that make sense? Does that make sense, guys? Any doubts, please put in the chat for problem D. Doubts for problem D. And what is the time complexity of this? Well, we just solved the equation using some formulas, and then we ran through all the elements and checked if the equation is matching. So it's just big O of n, right? If there's any doubts, please put it. Otherwise, we'll move on to problem E. So we just wrote these equations, assuming x1 operations of the first type, x2 operations of the second type. We simplified the linear equation and got x2 and x1's values like this. And then we tested whether x1 and x2 values are valid, like they're not fractional, they're not negative, and they satisfy all our equations. If all these cases hold, we print yes. Otherwise, we print no. Yeah, we don't care about 1 to n. It can only be 3 to n also. But then explain inside the loop. Okay. So what is going on inside the loop? I am checking if, now that we found the value of x1 and x2 using algebra, right? I am checking if AI, okay, if AI minus I times x1, right? Because we did x1 operations of the first type, minus n minus I plus 1 times operation of x2, right? If this is equal to 0. If it's equal to 0, no problem. But if it is not equal to 0, if it is not equal to 0, that means there is no solution to this set of linear equations, right? This was the original set of linear equations. So we're checking if x1 satisfies, x1 satisfies, x1 satisfies, x2 satisfies. Like we're checking whether x1 and x2 satisfy the whole set. Like we found x1 and x2 only using these two equations, right? But we must check if they satisfy 3, 4, 5, all the way till n. So that's why we're doing this. And we check if it satisfies or not, right? So if it makes it equal to 0, then it is a root. Otherwise, it's not a root. So that's why we're doing this loop and we're checking. Make sense? Yeah. Okay, moving on to problem E. I think we spent enough time on this. Lost soul. Okay. So this is also a bit constructive, slightly constructive problem, but I'll try to explain it the best I can. Okay. Okay. You are given two integer arrays, A and B, each are of length n. You can perform the operation any number of times. Choose an index I and set A of I equals B of I plus 1, or set B of I equals A of I plus 1. Okay. Before forming any operations, you're allowed to choose an index I and remove both A of I and B of I from the arrays. This removal can be done at most once. Let the number of matches between two arrays C and D be the number of positions such that C of j equals D of j. Your task is to compute the maximum number of matches that you can achieve. All right? Does that make sense? Yeah, E should be at least 14, 1500, I guess. No, I didn't do it with DP. I did a constructive slash greedy approach, but I'm not sure. Oh yeah, they even gave problem tags. It is greedy. Okay, so let's explore what the problem is telling us. Let's take an example in the from here, okay? So let's say we have our first array is 2, 1, 5, 3, 6, 4. Okay, this is A, and B array is 3, 2, 4, 5, 1, 6. Right? So now what our operation is, we can choose any index I, and we can set A of I equals B of I plus 1. So basically we can write this as 1 instead of 3. Right? So that's one way to do it. Another operation we can choose is write B of I as A of I plus 1. So we can change this to 6. So we can write 6 here. So this is the two given operations we're given. And our operation you can observe follows a zigzag pattern. Like if we want to set 4 equal to 1, right? Then we can set like this. This becomes 1. Then we can set like this and this becomes 1. So it kind of follows this zigzag pattern along the array. Okay, I hope that makes sense. So now what we want is maximum number of matching or maximum number of positions such that C of j equals D of j. Okay. Now I want to make one claim that when we find the first matching, we can stop. Okay, so this is my first idea. So observation 1, when we find the first matching, we can stop. Okay, so what we want to do is, how do I prove this? Proof. Let me tell you what we mean by we can stop, right? What I mean by we can stop is all elements before can also be made into matching. Okay. And how do I show this? Let me say, if let's say our array was something like this, uh, 5, 6, 7, 8, 9, 10, 10. Okay. So this is our first matching we found. The array continues. And then we have 1, 3, 2, 4, let's say 1. Okay. So now here we found a matching that 10 equals 10, right? Then all the elements afterward will also be matching. Why? Because simply we set the value here and we set the value here, right? So 1 equals 10 and we set 9 equals 10. Then we can set 4 equals 10, 8 equals 10 using this operations, right? And we can do as many operations as we want, right? Of this type. So here again we can set 10 and 10 and so on. We can keep setting until before the first point of matching, everything becomes 10, right? So everything will become 10 before the first point of matching. And so all of these will be matching, right? So our problem reduces to finding. Also, what I mean by first point is first point from the end. Okay. So finding first point from the end which can be made to match. Okay. So this is our first observation itself, right? Okay. Now what is our second observation? So I'll tell you what idea we're going to do. We're going to do a greedy idea. Okay. And our greedy idea is given, let's say, some numbers like 3, 7, 6, 5, 2, 8, 20, 30, 40, 7, 6, 3. Okay. And let's say we want to find the first point of matching for this. Okay. So what we will do is we will try to make it as far as possible, right? Because we want the first point from the end. So we'll try to make 8 and 3 match. Can we make 8 and 3 match? No, we cannot make 8 and 3 match because there is no operation we can do. There is no element after it. Correct? Can we make 2 and 6 match? No, there is no operation we can do and there's no element after it which we can use. Like even if we put the value 3 here or we put the value 8 here, nothing will be changing. Correct? And one very important thing I want to note is there's also this operation, right? We can perform a removal of some position from both arrays at most once. So for now, we are not thinking about it. Later, we'll come and think about this operation also. For now, we'll not think about it. Okay. So yeah. So what else? Um, let's try to make 5 and 7 matching. Okay. So what values can 7 take? Like I said, 7 can take either value of 3. So 3 value can be propagated here and then propagated here in a zigzag fashion, right? If we propagate the value of 3 like this, then 7 can become 3. Otherwise, the value of 7 can be 2, correct? So 7 can be 2 also. Similarly, the value possible here equals 5, 6, 8, and the values possible here equals 7, 2, 3, right? And there is no overlap again. So we can't make these two equal, right? Now at 40, the possible values go something like this, right? So in this zigzag pattern, all the values are available. So for 40, the values which are available are 45, 6, and 8, right? And here you observe that this 6 can be matched with this 6, correct? This 6 can be matched with this 6. So the idea is we first take these two equal. So we can make this 5 into a 6. Then we make these two equal. We can make this 5 into a 6. And now we got a matching. Now we found a matching. Now we found first matching from the end. From end. Now we can simply return the value. Let's say I equals 3, right? So we can have at most 3 matchings and we can simply return the value of 3. Okay. Does this idea make sense so far? Because since we are going in a zigzag pattern, right? Unless we directly get something like 6, 6, in which case it's directly equal. We can check all the elements in this zigzag pattern when it becomes equal. And whenever we find a matching, we stop it there and we say that these are the total number of matching elements we can make. Okay. And we go from n minus 1 to 0. Okay. How to implement this, I'll go on. But can you just tell me if this much idea is clear? Yeah. Okay. Now, how do we implement this idea? Well, we can simply have a unordered set, or we can have a normal set also, but that gives a log n. So I'll use unordered set for this problem. We can have an unordered set for zigzag, unordered set, which we can call zigzag 1, or we can call it alternating 1, and zigzag 2. Okay. So what will this set store? It will store all the elements which appeared in my zigzag. Okay. So zigzag 1 will store this value, this value, this value, this value. And maybe zigzag 2 will store this value, this value, this value, this value. Okay. So that way I can quickly check if, so based on odd and even, so whether my current I is odd and even, I can decide if A of I goes to zigzag 1 or zigzag 2, right? Or 2. Similarly, if B of I goes to zigzag 1 or 2, so it'll be opposite, right? It'll be zigzag 2 or 1, right? So if it's odd, we'll put A of I into zigzag 1. If I is even, we'll put A of I into zigzag 2. Fine. So that way we will get a simple zigzag pattern like this, right? So let's say the last element was a odd numbered element. So we'll put this A of I into zigzag 1, right? And then here it's even, so we'll put this B of I into zigzag 1, this into zigzag 1, this into zigzag 1. That makes sense? Then I can simply check if A of I present in opposite zigzag. Like if A of I went to zigzag 1, I need to check if it was present in zigzag 2, right? Opposite zigzag. So if it was 1, I need to check if A of I was present in zigzag 2. If it was 2, then I need to check if A of I was present in zigzag 1. Right? Make sense? Yeah. Thank you for that piece. So why am I doing this? Well, it's very simple. I'm checking if at any point it becomes equal. And like if I check for A of I, so here A of I is going into so let's say this is a odd position, right? So this is the third position. So I will check if there is 6 in zigzag 2. And we see that 6 is there in zigzag 2 because zigzag 2 came like this, right? So we can see 6 is there in zigzag 2. So I can say that, yeah, we can have a matching. So we can stop here and we can say that this much is matching. Right? Okay. So this is how to solve the problem. This is the idea of the problem so far. Idea of problem so far. Now we need to do idea of problem with deletion of one index. Okay. So now the idea of problem with deletion of one index, and this is part 2 of the question basically. So let's call this observation 2. And what happens when we delete one index? Well, let us consider general elements for now. Okay. B1, B2, B3, B4, B5, B6. Okay. So these are general elements for now. And let's say we are at some position here and we are trying to see a matching. So first thing, we obviously compare the zigzag values. So we compare if this equals A3. So that was not true. Okay. Then we compare this zigzag values. So we check if this equals B3. And let's say that was also not true. Now we think, can we use deletion operation somehow? Okay. And I'll show you how to use deletion operation. So the idea is we will delete this. Okay. And what does this do? What this does is if we delete this, then our zigzag pattern becomes like this. Okay. So B3 goes to A3 and B6, right? Earlier, what was B3 going to? Earlier, B3 was going like this, right? Now, what is happening after the deletion? So before the deletion, I wrote in green. After the deletion, B3 goes to A5 and B6, right? So the pattern has changed and it has in fact become the opposite pattern. Become the opposite pattern. Like we can now make this B value equal to any of the opposite numbers, right? Not counting I plus 1 because I plus 1 got deleted, right? So these values got deleted and the pattern became the opposite pattern. Is that understandable? Yeah, the zigzag set changes. In fact, it becomes the flipped set, right? So basically zigzag, if this was zigzag 2, let's call this zigzag 2, right? Then what happens is we basically get zigzag 1 itself. We get zigzag 1 itself, but this value gets skipped. Does that make sense? This value gets skipped and we get zigzag 1 itself, right? Because what was values of zigzag 1? Values of zigzag 1 went like this, right? So we got all the values of zigzag 1 except this. So for zigzag 2, we get zigzag 1 except the previous element. And for zigzag 1, we get zigzag 2 except the previous element. Understood? Yeah. So what we can do is there are many ways to try. Okay, so first we will try normal zigzag, then we will try the deleted zigzag. Okay, and then many ways to try. One way is to simply make 4 sets. Simply make 4 sets to keep track of all the possible ways. Okay, to keep track of all possible ways. And that is also a perfectly valid way to implement. Okay, keep track. Zigzag 1, zigzag 2, old zigzag 1, which does not include I plus 1, old zigzag 2. Okay, so that is one way to do it. The other way to do it, which is what I did, it was slightly complicated because it was in the contest, but yeah. So what I did was, is, instead of inserting into zigzag 1, instead of inserting, so this is what I did, my implementation. So now we understood the idea, we just need to implement it somehow, right? So my implementation was, let me write in a better color. Instead of inserting A of I, inserting A of I immediately into zigzag, I go to the next step. Okay, I go to the next step. Like, let's say when I'm here, I don't instantly insert this into the zigzags. I go here, I check my opposite zigzag values, right? Then I insert I plus 1. Then I insert I plus 1. Then I check the normal zigzag values. Do you understand? So instead of inserting immediately A of I into zigzag, we go to next step, check opposite zigzag values, Then we insert A of I plus 1. So we insert the element earlier, which we did not insert. Insert A of I plus 1. Then we check normal zigzag values. Does that make sense? Because I want to check without if I deleted this element, right? So I want to check if I deleted this element, right? So first I'll go to the next one. I'll check if I deleted the element, like that deleted case. Then I will insert I plus 1. Then I'll check again. Does that make sense? Understood? Right. So here I named zigzag 1 as alternating 1, alternating 2. So that's why I named it like that. Unordered set alternating 1, alternating 2. So let us go through the code. So we want I. Why do we want I? Because that's the smallest element from where we can start our matching. Okay. So the idea is mostly done. We're going to go to the code now. So we'll do y I greater than equal to -1. Why did I do this? Just for implementation, you can write greater than equal to 0. And you can write an if case here also. So what I do is if A of I equals B of I, then we can just break because we know that now we have found a matching, right? If at any point we could remove the I minus 1 check condition and add element back. Yes, we can remove it and add it back, but for that we need to use a multiset, right? What if a value appeared twice? So for that, instead of unordered set, we can use unordered multiset and we can do it. Oh yeah, we can use hash map as well, actually. Yeah, we can use hash map as well. To be honest, unordered set is also hash map itself. So technically, both the ideas are the same. So yeah, you can use hash map as well, okay? So first we check if two elements are same. Then based on odd and even, our zigzag values become different, right? So based on if it's odd, we insert A of I into zigzag 1. Sorry, we count if A of I is there in zigzag 1 or if B of I is there in zigzag 2. If it's there, that means we found a matching, right? So whenever we're doing break, it means we found a matching at position I. Found a matching at position I. Because A of I was there in zigzag 1, right? Similarly, if B of I was there in zigzag 2, we can break. So this is for the opposite case, right? This we are checking the opposite case. Then we're adding A of I plus 1. Then we're adding A of I plus 1, B of I plus 1 into the correct values of zigzag. Then we're checking the normal case also. All right. So if any time we find a matching, we simply break and we can output I plus 1 as our answer. Okay. So similarly for the odd case, here this was the even case. For the odd case, it's the exact same code, but alter 1 and alter 2 are flipped. Right? It'll become alter 2, alter 1. So it's the exact same code, but I gets flipped. And that's all. If I equals -1, that means there was no matching at all, and the answer becomes 0. Otherwise, there was some matching, and the answer becomes I plus 1. Okay. I hope this is understandable. Yeah. Yeah, Dev Mehta, now that I read your comment, that actually seems much simpler actually, but I did not think of it in the contest. So I guess I complicated this explanation, but yeah, nice idea, Dev Mehta. That was a really cool idea. So except the element which is diagonally opposite, we can take everything. Makes sense. Okay. Hi, I solved 4 questions. Okay, Rishabh we just have one more question left, problem F. After the problem F, we will discuss general doubts. Okay. Just a pupil now. I am not sure since I cannot see your code. It depends on how you calculate because there are many possible implementations. So I'm not sure until I see your code. But yeah. As for Rishabh, I will answer your question after we finish F because I said general doubts after F. Okay. Let's do problem F. Um, Yusuf has a rooted tree consisting of exactly n vertices, which is rooted at vertex 1. Okay. And yeah, for this time complexity is big O of n. Since unordered set is a hash map, it works in big O of n. It can be n or n log n, whether you use sets or not. Okay. Problem F. Okay. Yusuf has a rooted tree consisting of exactly n vertices, which is rooted at vertex 1. We would like to give Yusuf an array A of length n, which can be either 1 or 2. Okay. So each value can be either 1 or 2. Let S of U denote the sum of A of V, where V is the subtree of vertex U. Okay, so normal definition of subtree. Let S of U denote the sum of all A of V, where V is in the subtree of vertex U. Yusuf considers the tree special if all the values in S are pairwise distinct. That means all the subtree sums are distinct. Okay. Your task is to help Yusuf count the number of ways that array A can be making a special tree. Okay. So number of different ways that A can result in a tree being special. Two arrays B and C are different if there exists an index I such that B of I is not equal to C of I. If the answer is very large, we can print it modulo 10 power 9 plus 7. Okay. So what does this mean? Let us take their example itself. So let's say we have a tree, right? We have some tree and 4, 5, 6, 7. Okay, so this is some tree, right? And basically we have an array which assigns values to each element, and the possible values which can assign are 1 and 2, right? It says our array values can be 1 and 2. So let's say we had some values like this: 1, 2, 2, 1, 2, 1, and let's say 2, something like this. Okay. Now what do we want? What does the question want? It wants sum of subtree. So for each subtree, so this becomes one subtree. These two together will form one subtree. Then subtree of 2 will be all of this, right? Subtree of 3 will be all the elements here. Subtree of 1 will be simply all the elements. So each should give a distinct sum. Each subtree should have distinct sum, right? And that is our question. So we're given a tree. We can assign value 1 or 2 to each node. Each subtree should have distinct sum. Find the number of ways to do this, right? Find number of ways to do this. All right. And we know that the root is at vertex 1. So that also is given to us. Okay. Yeah, easy F is possible. Yes. Yeah, it's easy F itself. So, but we simply don't need to tell if it's possible or not. We also need to tell the number of counts, right? Right. So we need to, yeah, going back to the problem. What idea do we get here? Okay. So what idea can we get here? And first we'll simply try by experimenting. Okay. Let us experiment on some trees. Experiment on some trees. Okay. So let's say I have a tree, something like this. Okay. If I have a tree, something like this, and this is my root. Okay. This is my node 1, which is my root. Then observe that each value can be at least 1 or 2, right? So then the sum of this subtree is 1. The sum of this subtree is 2. But then this leaf node also has to have value either 1 or either 2, correct? This leaf also has to have value either 1 or either 2, correct? So therefore, this will either be clashing with this, or this value will be clashing with this value. So immediately we get at most 2 leaf nodes. This is our first intuition, we could say, intuition 1. And our intuition is there'll be at most 2 leaf nodes possible. Why is that so? Because if we have more than 2 leaf nodes, our only allowed values are 1 and 2, so there'll be at least one clash, right? We can say by pigeonhole principle there'll be one clash. If for 3 leaf nodes or 3 or more leaf nodes, we try to fill with 2 values, correct? So that is our first idea. At most 2 or 1 leaf nodes. Okay. Otherwise, number of ways is 0. Okay. Yeah. It was much easier than normal F, I think. A lot of people might have not done it simply because it's the F problem, but it was very simple. Okay. Now, if there is at most 1 or 2 leaf nodes, what can that mean? What kind of graphs can we get? So if it's only 1 leaf node, then a graph which we can have will be simply line graph. Okay. So the graph which we can have will be simply a line graph like this. It need not be 1, 2, 3, 4, 5. It can be 1, 4, 3, 2, something like that also. The node order does not matter, but it is a line graph. Okay, so this is with 1 leaf node case. 1 leaf node. Okay. And then if we have 2 leaf nodes, right? If we have 2 leaf nodes, then there will be some point like 1. And then there'll be some branching point here, let's say like this, right? And then, so these are like the 2 possible types of graphs which we can get. Also, we can get a graph for 2 leaf nodes, which is something like this, right? One graph is like this, maybe. So root node itself is the branching point. And this is also basically the line case itself, but yeah, this is also one kind of graph, right? Actually, this is not the line case. This is different from the line case. Sorry. But yeah, this is the two cases we have. Either it's a line graph, or a graph with one branch. So we're considering this also as a graph with one branch, right? line graph, and here it's a line with the center node as the root node as the starting point, right? So if we have a line graph or line tree, what is our possible answers, right? So we'll simply get the answer for this very fast. The line graph's answer is simply 2 to the power n. And why is that? Well, look at this. The subtrees, the possible values of last node are 1 and 2, right? Now, what will be the possible values of this, right? We want subtree sum to be unique. But the thing is, each subtree sum will be value at I plus subtree sum of children of I, right? Child of I, right? So what is happening is basically this thing is adding this. Like if there was some value x over here, if there was a value x over here, then subtree sum will be x. If there's a value y here, then subtree sum will be x plus y. And we can see that since x and y are 1 and 2, right? So we will have that x plus y will never equal x, right? X plus y will never equal x. Similarly, if the value here was z, then the total sum for this subtree will be x plus y plus z. And we can see that x plus y plus z will never equal to x plus y because each value is 1 and 2, right? So each value will be 1 or 2 greater than the previous value. I think that should be understandable. So basically all choices of array are possible. We can use 1 or 2 here. We can use 1 or 2 here. It does not matter. All the subarray sum, all the subtree sums will be unique anyways. So the answer in this case is simply 2 to the power n mod, like percentage mod. So the answer will simply be this. This case is understandable. Yeah. So this case I think should be understandable. Now we'll take the branch, single branch case or Y-shaped tree, whatever you want to call it, right? Where there are 2 leaf nodes. So now we will check the Y-shaped tree case. Okay. So let us quickly revisit what we saw. So we saw that more than 1 leaf node cannot be possible. So we can call this observation 1. Observation 1. Sorry, more than 2 leaf nodes is not possible. Answer will be 0. Observation 2 is for only line case. The answer is simply 2 to the power n percentage mod. Correct. Now for the Y-shaped tree case. This is going to be our third case or observation 3 or whatever you want to call it. And with this, we will solve the entire problem. So let's say we get a branch over here. Okay. Something like this. Okay. Now, let's say at this point of the branch, this leaf. Okay. At this leaf, the value has to be either 1 or 2, right? Right? Either it's 1 or either it's 2. Okay. Let us assume its value was 1. Okay. And what happens is, once we fix the value of this as 1, right? A lot of other values also get fixed. And I'll show you how. We fix the value of this as 1. Then this one's value must be 2, right? If this one's value was 1, then there would be a clash, correct? So the number of ways does not change. This one's values become 2. Okay. Now what happens? If we put a 1 here again, then these two's value will become 2, right? This subarray will become, this subtree will become 2. And here we already have a 2. So we can't have that. So then this one's value becomes 2. And so the subarray sum becomes 3, right? So I'll write in green the values and I'll write in orange the subarray sum, the subtree sum. So the subtree sum is 1 here, 3 here, and here the subtree sum is 2. Now coming back, if we write the value as 1, what happens to the subtree sum? The subtree sum becomes 3. So again, there'll be a clash, right? So the only possible value of subtree sum over here is 4. And for that, the value must be 2 here, right? Similarly, what must be the value here? If we add 1, then again the subtree sum becomes 4, right? And we will have a clash. So the only value possible is 2. Okay. And now we have already come to the end of this, right? Now here, the subtree sum becomes 5. And now if we add a 1 over here, the subtree sum here will become 5. We don't want that. We want the subtree sum to be 6, which is a new value. So here also we add 2. Okay. So now we have ended this branch, like this branch is over. right? Now here it does not matter what sum we have. We can have 7 or 8, it doesn't matter, right? Because there is no clash. So there are two options. There are two options for 2 and 1, right? And the number of ways to do that is subtree sum of 7 or 8, right? Then again we have two options, which is 2 and 1 for this, right? Here also we get two options. Here it becomes the same as line case basically, since this is just the sum of the subtree plus 1 or 2. So here it just becomes 2 to the power n. So basically, once we have reached the end of one side, right, then this can be 7 or 8. This can be 8, 9, 10, 11, right? These become the possible values, right? So this can be 2 or 1, this can be 2 or 1, and so on. That's what happens. Possible values are 1 and 2, possible values are 1 or 2, possible values are 1 or 2, and all these possible values will give valid tree. And why will it give valid tree? Because see, now that this side the subtree sums were at most 5, right? So now we can, and this side the at most the subtree sums were 6. So now the subtree sum increases like 7, 8, then it becomes 8, 9, so on. It goes up like this. So there's never a clash because each sum is larger than the previous one. So basically what our answer is for this case, so for this case where we had 1 over here. So what is the case? The case where we started with 1 over here, right? So the answer for this case simply is, for this there's 2 to the power till the branch. Till the branch there are 3 nodes, right? So let's call that branch count. So there's 2 to the power branch count ways times this thing. So what is this? This is 2 to the power. Let's say in my left branch I had L count. So in my left branch I had L count values. So this is L count 3, okay? 3 values. Here I had R count 5 values. Okay. So I'll call this R count and L count. So R count is 5 and L count is 3. So the number of ways for this becomes absolute value of L count minus R count, right? Because there are two options for this, two options for this, and so on. This gives a multiplier of 2. This gives a multiplier of 2. Two options, two options. And over here, 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 if we fix this first value as 1, then we have only one option. Does that make sense? Okay. So in this case, this is the answer. Now let us talk about the complete different case. Okay. So we already found the, if this was value 1, if this was value 1, then what is our answer? So this is case 1, okay? If this node was value 1, our answer is simply 2 of branch count times 2 of absolute value of L count minus R count, number of ways. Okay. Now case 2, if this value was 2, okay? If this value was 2, okay? And what happens in this case? We have 2 over here. The subtree sum is 2. Then over here we need 1. We cannot have 2 because then it will clash, right? So we need 1. Here the subtree sum is 1. And here we'll see very similar pattern, but opposite. Now here we cannot, so here, let's say we can have, what do you say? Here we cannot have 1 again, right? So in this tree itself, you see, we cannot have 1 again because otherwise this 2 will clash, right? So here we have 2 again, right? And so this also gets fixed and the sum becomes 3 over here. Okay. Now here if we put a 1, here if we put a 1, then the sum for this node becomes 3. Then again there's a clash. So again this value becomes fixed as 2 because that's the only way we can do it. And then this value becomes 4, correct? Now if that is 4, then we can't add 1 over here, otherwise this value will also become 4. So we have to add a 2, we have to add a 2, and this value becomes 5. Is this understandable? Yeah. So going on, this will also become 2, this will become 6, right? Now we reach this point. So here we can't add both 1 and 2. Pay observation, pay close attention. Here we can't add 1 or 2, we must add 2 because 6 is already made. So in this case, this will become 7, right? This will become 7. And after this point, we're free again. We're free again. So this was 2, 2, 2. This was 1, 2, 2, 2. And after this point, we're free again and we can choose any values we want. This can be 1 or 2 because now Both 8 and 9 are possible sums, right? Similarly, this can also be 1 or 2 because once 8 and 9 are made, we can make 9, 10, 11. It will not have any clashes, right? Because it's the sum of the previous one plus 1 or 2, similar to the line case. So then number of ways becomes, this is your branch count. So number of nodes here is your branch count. It becomes 2 to the power branch count plus this value, which is how much? It is left minus, so this was left and this was right. So it is 2 times absolute value of left minus right minus 1, right? Because the first, um, if left is smaller, then the first L values were fixed here, and the first L plus 1 values were fixed here. So left plus right minus 1, these values are left to be free, and those can have either value 1 or 2. So there are 2 ways for those. So we get 2 into 2 into 2 into 2. So 4 ways for this case, right? Here the branch count is 3, left minus right minus 1, absolute value is 1. So the answer will be 2 to the power 4 for this specific case. So our case 2 is 2 to the branch count times 2 to the absolute value of left count minus right count minus 1. Okay. And what happens if they are equal? If left count and right count are equal, then we simply do not consider this case. Okay. Like we simply don't need to consider this term, right? We can just ignore this term. You won't divide by 2, right? So this must be at least greater than equal to 0. Fine. This value should be greater than equal to 0. In that case only we consider this. So these are our 2 cases, and our final answer will simply be, so once we find the branch point in the graph, we need to find the branch point. We need to find how much distance to the branch point. Then we need to find how much L is, how much R is. Okay. So this is going to be our solution. Find distance to branch point to branch point. Okay. And we will also count B count, which is number of nodes to the branch point. B count is number of nodes till the branch point. Nodes till branch point. Right. And then L count will be the left side from the branch point. Left side nodes count. So left side count. R count will be right side count. Say exact same how I explained. Okay. And what will our final answer be? It will be sum of these 2 cases because this value is either 1 or 2, and we saw what happens if this is 1 and this is 2. So the answer will simply be the sum of these 2 cases. So answer is 2 to the power branch count times 2 to the power abs L minus R. So L count minus R count plus 2 to the power. Okay. If this is non-zero, so this value will only be taken if non-zero. Otherwise, this will be taken as 1 itself, right? Otherwise, this term will become 1 itself, because if L was equal to R, then the last value will not be changeable. So this value will simply be taken as 1. Okay. If this becomes -1 or if this becomes 0, then this will simply be taken as 1. So 2 to the power 0, something like that, right? And that's all. This is our answer. So now we need to figure out how to find branch count, L count, and R count. For that, we're going to do simple algorithm. Simple algo to find B count, L count, R count. Okay. So do a DFS to find children of each node. Okay. Do a DFS starting at root. So we need starting at root. Each node. Okay. The branch point. Branch point. What does that mean? It's a node with 2 children. Okay. So that's the node with 2 children. Node with 2 children. We can count how much time it takes to reach such a node with 2 children. Okay. Then we can go left of branch point, go till we reach a leaf. We can go right of branch point, go till we reach a leaf. Okay. Go left and right till we reach a leaf. So the implementation looks long, but it is pretty simple. The idea is pretty simple till we reach a leaf. then we will get our L count, R count. We can use this formula to find the answer. To recap, if there are more than 2 leaves, the answer is 0. Okay. If there is 1 leaf, then the answer is simply 2 to the power n percent mod. If there's 2 leaf nodes, then we do this. And the way I am checking leaf is if there are ever more than 2 branch points. So more than 2 branch points, right? Let's say there were more than 2 branch points, like our graph was something like this. Like our tree split here, then again it split. So there's leaf, right? So if there are more than 2 branch points, or if there's a branch point like this, so it has 3 children. So if children is greater than 3, or number of children equals 2 occurs more than once, right? Then we can say that there are more leaves. So in that case, I print 0. Okay. And if there are no branch points at all, if the number of branch points are 0, in that case, I can simply print 2 to the power n percent mod, right? Otherwise, we do the formula. Otherwise, use the formula for y shape, and this is the formula. And of course, we need to calculate all of this percentage mod, right? And print the answer. Yeah. No, actually, I did not solve G during the contest. And although I have a vague idea of how to solve G, I don't want to talk about it right now in case my idea was wrong. So yeah. Yeah. So there are many ways to find branch point and all. So you do whichever way you're comfortable with. I'll show you my code so that you can understand it. Yeah. So first I defined the mod. Okay. Here is my DFS function. What does it do? It takes adjacency list and it converts that to children. So for each node, I have the children of that node. I want to see the children of that node to make my implementation easier, right? So that's why for each node, if it's equal to the parent, I just continue. Otherwise, I push back the children and I do DFS on the children. Okay. So very basic DFS. Here I'm pre-computing the powers of 2 given the mod, right? I don't want to recompute powers of 2. So I will just pre-compute all the powers of 2 all the way to 2 to the power 10, 2 times 10 to the power 5. Or here I did 3 times 10 to the power 5. So that way I have powers of 2 already pre-computed whenever I need them with respect to mod. Okay. Now I take in my input n, I take in my adjacency list, I do a DFS, correct? Then here is the cases which I mentioned. So NP means not possible. That means there are 3 leaves. And line case, so initially we set line case equals true. So if ever any node has more than 3 children, that means it's branching into 3 different points. So the number of leaf nodes will be at least 3. So then it's not possible, right? And if it's not a line, that means there's already a branch, and then we find another branch, right? So if we find 2 branches, like if we had 2 branches, like I explained, more than 1 branch point means either we had something like this, or if we had 2 branches, then again, here and here was branching. So we can say that it's not possible again because there'll be 3 leaf nodes. Otherwise, oops, just a sec. Yeah. Otherwise, it's possible, right? And then if ever the children size has more than 2, more than equal to 2, that means it's not a line case, right? That means there's a branch point. Okay. So if it's not possible, I simply print 0. If it's a line case, I simply print power of 2 and then I continue. Okay. Now I've already calculated my children using that DFS, right? So what I do, I'm trying to find branch point. I set my branch point as 0 and I keep going until the children's size becomes 2, right? Then I'll find my branch point and I'll find the branch count. Then my left will simply be from the branch point, the left child, and then the right child will be from the branch point, the right child. I have left count equals 1, right count equals 1 until I reach a leaf node. So until the children become 0, I increase my left side. Similarly, I increase my right side. Once I have reached that, I got branch count, left count, right count. I calculate the formulas which I used. So V1 is simply this term. Okay, V1 is this term in my formula. This is V1 term. Okay, and this is V2 term. So initially V2 equals 1, right? But if the absolute value difference between L minus R is greater than or equal to 1, so if this value is greater than or equal to 1, L minus R is greater than or equal to 1, that means that L minus R minus 1 is greater than or equal to 0, right? So then this case becomes valid. So in that case, V2 becomes L minus R minus 1 to the power of 2, right? So this is how I find V1 and V2. Then my final answer is simply V1 plus V2. I take mod to the power of branch count, right? So if you see, it's the exact same formula. It's this exact same formula, simply implemented using modulo arithmetic. Okay? It's the exact same formula I wrote, simply implemented using modulo arithmetic, and then I print my answer. Okay, so is that understandable, guys? Yeah, now it's quite easy, I guess. Okay, so that was all the solutions from A to F. Any doubts you can ask related to the problems or general doubts also. I am available for any general doubts regarding CP, regarding your practice, regarding what you should study, anything you want to ask me. Um, General doubts. Oh yeah, time complexity. The only thing we're doing here is DFS, and then we're just going traversing the tree. So the time complexity of traversing a tree is simply big O of n. Okay, so from the previous question, the time complexity is big O of n. Okay, it should be n plus m for DFS, but number of edges in a tree is simply n minus 1. So we can simply write it as big O of n. Okay. Your implementation is very clear. Can you give some tips for this? Okay. So for that, the only thing I can say is, first of all, if you do more problems, after a while, your implementation becomes clearer, right? So with practice, your implementation becomes clearer. The second thing about implementation is, instead of coding immediately, right? Usually you get the idea. Instead of coding immediately, wait 2 to 5 minutes and try to think of better implementation. And why is that? Why you should wait 2 to 3 minutes, 2 to 5 minutes, and then implement? Because then you can find some simpler implementation. And what happens is, not only do you code faster, but you make less bugs. Because if your implementation is simple, you will make less bugs. So definitely spend some time thinking about the implementation using pen and paper before implementing. One more reason I can say that the implementation is clear is because I knew I had to do PCD, so I didn't hurry during the contest. I did it slowly so I could solve and write decent implementations. Okay, can someone tell me what to learn, DP or graphs? So my honest suggestion is, do it parallelly, right? Like DP and graphs, you can do in a week, maybe 3 days DP, 3 days graphs, because that's how I learned personally. But it doesn't really matter. You can do either way. You can do first graphs, then DP, or first DP, then graphs. But yeah, it depends on which resource you're following. If you're following TLE Eliminators, then I guess graphs occurred first. I'm not 100% sure. But yeah, the correct answer is doesn't matter. Just learn both. Learn some DP, learn some graphs, then do more advanced DP, do more advanced graphs. That's how you have to do it. Okay. I solved 4 questions, C and D with one wrong submission. Right. I am 1285 currently. Yeah, I think if you solve A, B, C, D, then I think your performance for a pupil is decent, right? So I think your performance is perfectly fine, Rishabh. Although if you want to improve this, then you should solve maybe, I think around 1400, 1500 rated problems you should do, right? Rishabh, you should do like 1400, 1500 problems. Yeah. Here is the code I was confused about earlier. Okay. So checking a code live right now will be a bit of trouble. So just a pupil now, please just put it in the YouTube comments. Afterwards, maybe tomorrow I'll check it. Okay, I'll check the code. Or if you're in TLE, then you can just make a new doubt. Either me or some mentor will answer it. Okay. Projects in ML or web dev. Okay. So this is a CP channel. So I can't really tell you. That's up to you. What do you like more? Do you like ML? Do you like statistics? Do you like training data to ML? Or if you like web development, if you like seeing your results immediately, web dev is very responsive. You can get your answer instantly whether it looks nice or not. Then if you like that, do web dev. I actually don't. I don't think it really matters. Choose one. Choose both. Try both paths and see what's best. This is a CP channel, so I can't really help you with that. I have done DCA to Striver sheet. Okay, right. So I think if you are struggling with bottom-up DP, then what you should do is try the CSCS DP problems, right? If you go to CSCS website, uh, CSCS website, okay? So if you go to DP here, there is a bunch of problems here, right? Which are very hard. Like even if you do half the problems, that's fine. Do even half the problems. Like I think I have done till somewhere here, I guess. But yeah, these are very nice, very classic problems. They'll teach you a lot. Other than that, of course, TLE level 4 has DSA and a lot of DSA problems. So you can definitely check out TLE level 4. So Nit, same question about DP. So yeah, I suggest watch some video on DP, right? Like Ericto's video or something like that. Then do CSES problems. You can also read Competitive Programmer's Handbook, which I found very nice. Of course, the TLE level 4 course covers DP in detail. So I can show you that already. If you don't mind buying the course, then yeah. Like personally, I've gone through the course. It's pretty nice. It's pretty much exactly what a person who's new to DP can learn, right? DP, everything from recursive versus iterative to standard problems, general techniques, all those stuff is there, right? Okay. Yeah. So Harpenstein, yeah, you should practice a good level of till 1300, and then you should move on. Is backtracking important? Yeah, you should definitely know the idea of backtracking, and ideally you should be able to, recognize when a problem uses it. So I think at 1300, definitely you should know backtracking. Can you share your CFID? My CFID is Accord. You can go check it out if you wish. Right? I'm in fourth year and I just started with CP. I'm enjoying it more, and this might hamper placements which are in 2 months. Should I focus on DSA or core CS? Will CP be helpful? Okay, look, if you had no CP experience before, then right now getting into CP might be slightly detrimental. But uh, yeah, so what you should do ideally is do DSA, do your interview practice. So lead code style questions are more close to interview. So I guess you should try lead code more, I guess, Saikat Mandal. So try lead code and you can do CP from time to time, right? Doing contests never hurts anyone. So definitely if do all the like if do at least one contest a week, maybe one contest 2 weeks, that's fine. You can watch these upsolving videos. Other than that, I think you should focus more. If your DSA is weak, if your DSA is already weak, then in your interviews they will ask you DSA questions, right? So first you should have that down before getting into CP, because CP is after you know some basic DSA and then you want to become good at problem solving, right? But yeah, a healthy mix of both is good. How am I preparing for intern next sem? To be honest, I'm just following my college course and like I'm doing Codeforces. I'm trying to like go to like last time I went to ICPC regionals. So this time we got some. Last time we got a rank of like all India rank of 50 in Amrita. So I'm just preparing for ICPC and hoping that that covers my interns. My rating was almost. Look, what would be a good score in lead code contests? That depends on you. Okay, Rahul Arora asked, what is a good score in lead code contest? Depends on you. In the start, everyone solves only one problem out of four. Okay, when you're just starting out, everyone is that at that same stage. Okay, so what you should do is you should always practice of the level of the second problem. Since you could solve the first problem, right? Always upsolve one problem which you cannot solve. Okay, so here is my first piece of advice, most important. Always upsolve the next problem you were not able to solve. Okay, you were not able to solve. Okay, and this is very important because this helps in a lot of growth, right? So whichever problem you got stuck in a contest, you should definitely upsolve that. So, and eventually you will be able to solve second problem. Then you'll start getting stuck at the third problem. So you can upsolve that. Okay. Mm. If your rating is 1360, then definitely I guess you should start maybe TLE 1400 rated problems. This is for Sonit Raj. If you have solved up to 1300, then start 1400 rated problems. Or if it's not easy, then 1500. Just a pupil now. If your rating was almost 1500, but last five contests went really badly, Don't worry too much, okay? Maybe there was some gap, or maybe you were sick, maybe your mental state wasn't that good, or maybe it was just bad contests, okay? It happens. Like for me also, 3, 4 contests in a row, I just lose rating. Sometimes it happens, okay? Don't worry too much about it. You were already almost 1500. That means you were almost, you were specialist. Um, so definitely you should not have much problem. Just keep practicing. You'll get back to it. I'm not a student, but I love doing CPDSA for fun. So it's tough to manage with work. Thank you for the solutions for lead code and safe. Well, I'm glad you liked it, Parth. It's nice to see that people who are doing work also still do CP because of the love. That is amazing. I also hope that, when I get a job, I still do CP because I'm very invested. That's great to see that people still keep this hobby. Yeah. Yeah. Okay. Nice to hear that, Psychic. All right, then. If we don't have any more doubts, we will end the session now. I hope the session was understandable. I know that in the first problem there was some internet issue, so I sincerely apologize for that. Again, I recommend you to check out TLE's self-paced course. Based on any level you are at, see which level you are at. If you feel like a complete beginner, if you feel like you need to learn these concepts, prefix sum, bit manipulation, then you can go for level 2, level 3, level 4. And then you get dedicated doubt support, which I think is the best thing out of all of this. The best part, maybe in the video lectures, practice problems, is the doubt support. Because within 15 minutes, you can, if you're stuck at a question at TLE, you can get, you know, yeah, if you're stuck at a question at TLE, you can just make a doubt support, and a mentor like me or someone with, roughly my rating, who's definitely expert plus, will be there to help you out. Yeah, even if you're stuck in implementation, doubt support helps you. Nowadays, lead code Q1 is medium. Yeah, over time, the problems become harder. People get bored of easier problems, so they start medium. Some people are good without much practice, but some require more time. It's simply because it matters on the prior background, right? Some people were very good at math earlier. Some people were very good at puzzles. They just used to watch TED as a child a lot, maybe, and they used to do those puzzles on the TED YouTube. You'd never really know, right? So everyone has their own level, but one thing is for sure, if you put in enough practice, you will definitely become better, right? Even if everyone's learning rate is different, if you put in enough practice, you will definitely become better. So don't see how much time it takes, see how much you can reach. Okay. Sir, are you a college student right now? Yes, I am a college student. I am currently I'm going to third year next sem. Yeah. Uh, at what level of performance in Div 2 and Div 3 should I start good concepts? So, okay, I think A and B in Div 2 are basic questions without any prior background required. And in Div 3, I think ABC or ABCD sometimes don't require prior background. Once you can solve ABC or ABCD in Div 3 and AB in Div 2, then you should start learning new concepts. Where did you learn CP? Did you also take the TLE course? So no, at that time I was not aware about the TLE course. Um, I I was a participant in Olympiads. So if you don't know or know, for 11th and 12th students, there's a competition called Informatics Olympiad. So I was a participant there, and I was national level medalist at that time. To become a national level medalist in Olympiad doesn't take that much effort because not many students know about it in 11th and 12th. So I did a little bit of it in 11th. In 12th, I didn't do much because of JE, because I was practicing for JE. But yeah, in 11th, I did a little bit. So that helped me. I learned my basic concepts in 11th. And then in my first year, I grinded a lot and I became expert in my first year. Yeah. Have you ever faced performance anxiety every single time I do a contest? That definitely happens. If you feel performance anxiety is troubling you particularly, then you should do virtual contests, because virtual contests are like mock contests and they help you a lot to manage the anxiety because you have the time pressure, you need to finish it. You can pretend in a virtual contest that your rating will drop, right? Then it gives you that anxiety. How many CSCS problems have I solved? To be honest, not that much. Um, I actually am not a person who solves much problems. My philosophy is that I will solve less problems and I will try to extract as much value as possible per problem. So you can see my profile. I guess I have solved like 80 problems here totally. Although to be honest, a lot of these problems have become very easy for me now. Like after doing so much Codeforces and ICPC practice, I think Many of these problems I can easily solve. I've not come back to it for a while. But yeah, this is roughly how much I've solved. Don't look at me. Um, Definitely most people need to solve more than this. Like I was preparing for Olympiad as well. So I used to solve the old Olympiad problems and that used to help me a lot. Right? It doesn't make sense for you to solve those right now because those are for 11th and 12th standard students. They're not really relevant for the general CP, but that helped a lot for this. So yeah, that's why my CSS is not that solved. But definitely my friends, if you see my friends' CSS accounts, who are also like my rating or expert or similar, you can see that they've solved almost all dynamic programming and they've solved almost all graphs in CSS. So yeah, where did I primarily practice? To be honest, my primary practice was Codeforces, the problem set, and virtual contests. That was my primary practice, which helped me the most. I went from pupil till mid-expert just by practicing Codeforces. Pupil to 1600 plus is 6 months. Yeah, that's definitely a good goal. That's a balanced goal. But again, it depends on your background. Okay. Yep. All right. I guess that's it. I know all concepts. Random problems or in a structured way. Well, I'll tell you what I did. Okay. So when I was in my first year, I used to get repeatedly stuck in C problems. Okay. So I used to get repeatedly stuck in C problems on Codeforces. And that was my level at that time. I could solve A, B in like 1 hour. And then C problem I could not solve. So what I did was I went like in a period of 30 to 50 days. Okay. In a period of 30 to 50 days, I just sat down and solved all the C problems, solved all C problems in the past, like in the past, in the past like 30 contests, which I had not done. Okay. And I just solved them one every day I used to solve. And then that taught me so much. Like if I didn't know a topic, I learned that. And also I learned dynamic programming and graphs. So I made sure that my basic concepts like dynamic programming and graphs were covered. And then I sat down and did all the C problems from like the past 30 contests because I was getting stuck there, right? And then that automatically made me solve C soon. Can we get the PDF? Yes, I will attach the PDF. Maybe in a 1 or 2 hours, like uh I'll tell admin of the YouTube channel to attach it. Yeah, RM. If you started just 3 weeks ago, then don't worry. Only A and B, if you're able to solve, that's perfectly fine. That's in fact good only that you're able to solve B also, because some people who start 3 weeks, they can't even solve B. So yeah, you can definitely check out TLE's course. It's oriented towards beginners. You can also, yeah, you can also do what I said, practice C problems, practice virtual contests. Where did I learn DP and graph, Aryan? I learned it from, I would say a mix of Ericto's videos and Competitive Programmer's Handbook. So there's this famous Competitive Programmer's Handbook, which comes, I think, by the same person who made CSS. They also made it, Competitive Programmer's Handbook. So mix of that and Ericto's videos and Codeforces, of course, and also did CSS side. Yeah. Yep. Yes, Rishabh, that's a great idea. If your main thing is web dev and you're doing CP as a side quest, then I think your performance is pretty good. All right, the video has reached almost 2 hours, more than 2 hours. So I think it's time to say good night. Good night and best of luck, everyone. Yeah, I first learned the topics and grinded. Not exactly. I did both of them side by side, to be honest. Like I kind of learned, yeah, but in the later part of my grind, I had already the topics down and then I had grinded. Yeah. All right, good night, everyone. Hope you enjoyed the solutions. Thank you very much and see you next time. Good night.